In this video, we're going to work on problem 3 of the chapter 3 in-class problems worksheet. And so in this problem, what we're dealing with is an ideal gas that's contained in a piston cylinder system. And this piston has a cross-sectional area of 0.1 meters squared. We're also told that the pressure outside the cylinder is 1 atmosphere. Initially, the gas inside the piston cylinder has a volume and temperature of 1 meter cubed and 25 degrees Celsius, respectively. And then the system is adiabatically compressed to a volume of 0.1 meter cubed. All right? And then assuming that this compression occurs in a quasi-static manner, we're asked to estimate the following properties, such as the initial pressure of the gas, the moles of gas that are in the system, the final gas temperature and pressure, and then the work that's exerted onto the gas from the surroundings. Okay? And so based on the text in this problem statement, what I want you to do is pause the video here and draw out a schematic of the system. And so based on this problem statement, we could draw a schematic of the system that looks like this. So we have some gas inside a piston cylinder setup, and it's horizontal, just to emphasize. And then this gas is compressed to a smaller volume. The initial volume is 1 meter cubed, the initial temperature is 25 degrees C, and the final volume that it's compressed to is 0.1 meter cubed. And also for this problem, just to sort of give us some values to work with, we're going to assume that the heat capacities of the gas are constant, and specifically we're just going to use a value of 21.7 joules per mole degrees Celsius, which is a common value that you would see for gases like nitrogen. In any case, for this problem, we want to solve for things like the initial pressure, the amount of moles in the system, and the final temperature and pressure, and the work that's needed in order to compress the gas in a quasi-static manner. Okay? As far as things we don't know about the system, so specifically we don't know the initial pressure, we don't know the initial amount of moles in the system. We don't know the final pressure, which presumably is going to be greater than that initial pressure since we're compressing the system. We don't know the final temperature. We technically don't know the final amount of moles in the system. And we also want to figure out, I wrote it here as force apparent, but basically we want to figure out what is the work it takes in order to compress the system. Okay, so 1, 2, 3, 4, 5, 6. So we have 6 unknowns. So that means we need 6 equations in order to solve for everything. Okay, so this gives us an idea of, how many equations we need to use in order to fully solve this problem. Okay? Now before we go out and try, applying various equations to solve this problem, we should list various assumptions that we use in order to simplify the analysis of the system. Okay? So in the problem statement, we're told that the compression occurs in an adiabatic manner. And so that tells us that the heat in the system is going to be equal to 0. Okay? We're also, as is typical of thermal problems, we're going to assume changes in kinetic and potential energy are negligible. We're told that we're going to treat this gas as an ideal gas. So we'll make that assumption, and we'll invoke that assumption quite a few times during this analysis. And the last thing we're told, or we're asked to assume, is that this compression is quasi-static. Okay? And so we'll learn more about, what exactly quasi-static means in the following chapter. But effectively, what this tells us is that the system is essentially at equilibrium at all times, or equilibrium throughout the process. And so if it's at equilibrium throughout the process, that allows us to apply various equations of state to describe things like pressure, volume, and temperature. In particular, that allows us to describe the pressure of the system using the ideal gas law. Okay. All right, and so these are the list of assumptions that we're going to invoke for the system. And as far as the reference state is concerned, for the gas, we can just use those initial conditions. So Tref is equal to T1, Pref is going to be equal to P1. Even though we don't know the exact value, we could still say that we're going to use that pressure as a reference condition. In the reference phase, it's going to be a gas. Okay. All right, so now that we've kind of stated our assumptions and reference conditions, now we need to move on to applying our material and energy balances. And so for the material balance, we write accumulation is equal to input minus output plus generation minus consumption. No reaction going on in this system. And this is a closed system, so there's no inputs or outputs. And so this tells us that the final amount of stuff in our system, or final amount of gas in our system, minus that initial amount of gas, that's going to be equal to 0. Therefore, the final amount of gas in the system is equal to that initial amount. The initial amount of gas in the system in moles, we could say it's equal to N1. And that final amount, we could say that's equal to N2. Therefore, from our material balance, we get that N2 is equal to N1, right? And so that helps reduce the number of unknowns we have in the system, right? And so instead of N2 and N1 being different variables from our material balance, we could say that they're equal values. Now, of course, we still don't know what the numerical values of N1 or N2 are. But at this point, what we could do is we could attempt to apply the ideal gas law. Because we know for an ideal gas that the moles of the gas are going to be equal to PV over RT. Okay? But unfortunately, the issue here is that we don't know the pressure of the system. And so if we don't know the amount of moles and we don't know the pressure, we have two unknowns and only one equation. And so that means we can't just solve for the pressure directly from the ideal gas law. Rather, we're going to have to figure out the pressure of the system by doing something else. What we're going to do is we're actually going to consider the different forces that are acting on the system. Okay, so if we go to the next slide, or next page, for our piston cylinder system, the way we could get that pressure is by considering the forces that are acting on both the gas and that piston. Okay, and so in state 1, in the initial state, here's what the piston is, and we know that on the left-hand side of the piston, we have the gas in there. And those gas molecules, they're not static. They're not staying in place. They're moving around, right? They're constantly moving around, and occasionally they bump into the face of the piston, okay? And when they bump into the face of the piston, they, apply a force on it, okay? And so on the left-hand side of the piston, we have the force of the gas. On the right-hand side of the piston, we have the force of the atmospheric molecules acting on it. And so we know outside the piston, it's not in a vacuum. It's just in atmospheric pressure. And so that means that those air molecules or whatever, they're also kind of moving around and bumping into the piston as well and hitting it and applying a force on its right-hand side. Now, in the initial state of the piston, nothing is happening. Nothing is moving. It's just kind of staying still. And so if it's staying still, that tells us, that the force of the gas acting on the left-hand side of the piston must be equal to the force of the atmospheric molecules acting on the right side of the piston. Those forces are balanced, and so as a result, there's no net movement of the piston. Okay? So force gas is going to be equal to force atmosphere. Okay? All right, and so, this is our force balance. I should write it out here. And we're going to use this force balance in order to figure out the pressure of the gas on the left-hand side of the piston. And the reason for that is, I mentioned that the force of the gas is due to gas molecules, bumping into that face of the piston. And the way we could quantify the force gas is by saying that's equal to the pressure of the gas, P1 initially, times the area of that piston. So P1 times the area of the piston. For force atmosphere, the force that is applied by those atmospheric molecules is just going to be the pressure of the atmosphere times, once again, the area of the piston, because it's acting on the piston there. And so from our force balance, we have a relationship between the pressure of the gas inside the cylinder and the pressure of the atmosphere outside of it. Both of those are multiplied by the area of the piston, and because of that, we could just cancel out the area of the piston, and what we get is that the pressure of the gas inside the cylinder is actually equal to the atmospheric pressure. Okay. And so we're able to reason that. We're able to figure out what the initial gas pressure is just by invoking and using this force balance. Okay? And so that gives us part A. And so now that we've had part A, we can now go back to that ideal gas law. And we could plug in for P1. Okay? And if we plug in for P1, what we get is that the number of moles of gas in the system, I should write that this is equal to 1 atmosphere. Box that in further. If we plug in P1 into our ideal gas law, we get that the number of moles of gas in the system is 40.36 moles. Okay? So very simple way. All right, so that gives us the sort of initial conditions about our system. What we want to figure out next is now both the work and the temperature of the gas after it's been compressed to that new volume. Okay? And to approach this, what we're going to do is now we're going to move on to the energy balance for our system. Because we only care about, initial and final conditions, we're going to want to use, and we're dealing with a closed system, we're going to want to use the closed form, or the difference form of the closed system energy balance. Okay? All right, and so the closed form of the energy balance is du plus d kinetic energy plus d potential energy is equal to dq plus dw. We don't care about changes in kinetic or potential energy, and because the system's adiabatic, we don't have any heat that we need to care about. And so what we're left with is that du is equal to dw. Okay? Now, for du of the gas, we could write it in terms of the heat capacity, specifically the constant volume heat capacity. Right? And for the work, or dw, we could just use the general form of the work equation, which is negative force exerted by the system times some displacement there. Okay? Now, the force that we would put in here, this is the force exerted by the system. And so from our force balance, we know that that force is just equal to the pressure of the gas times the area of the piston times dx. Okay? Now, the area of the piston, that's a constant. So what we could do is we can move that inside of the differential. And when we do that, we know that area times the displacement gives us volume. And so what we get is the internal energy, or the left-hand side of the equation, is now just equal to negative P gas times dV. Okay? And so that's all just from manipulating the energy balance. Okay? All right. And so as far as the we have this statement here. We know this, and we want to figure out temperature. And we already know how volume changes. We know what the initial and the final volumes are. But what about this P gas? What are we going to do here? Okay? And so because, this is where we invoke that assumption that the compression is going to be quasi-static. All right? And so when compression is quasi-static, that means it's happening so slowly that you could treat the system as being at equilibrium at all times. And so if the system is at equilibrium at all times, that means that we could describe the pressure of the system, the pressure of the gas, by using the ideal gas law. Okay? And so this is in contrast to, practice quiz problem 1, where the compression was happening so rapidly that the pressure or the force that was acting against the gas was constant. In this case, the pressure of our gas is going to be changing as the volume of the system is changing as well. Okay? And the way we describe that change is by using the ideal gas law. Okay? And so what we could do is we could plug in the IG law into P gas. And so this is just kind of a general NR T over V. But what we know is that N here is just equal to N1. We know that the moles in the system are going to be constant. And so that allows us to cancel out the N's on both sides of the equation. And what we're left with is CV dt is equal to minus RT dV over V. Okay? All right? And so what we could do here is we essentially have, this sort of differentials, these derivatives on each side. On the left-hand side, we have the derivative with respect to t, and on the right-hand side, we have the derivative with respect to volume. And what we could do is, since this is essentially a separable differential equation, is we can move all the t stuff to the left-hand side and keep all the v stuff on the right-hand side. And I'll also divide both sides by the constant volume heat capacity. I'll put all the constants on the right-hand side. Okay? And so here, we have this differential equation, and I'm going to call this equation 1, because we'll come back to it later. Okay? In any case, what we could do is we could integrate equation 1. So if we integrate dt over t from t1 to t2, and we can integrate dv from volume 1 to volume 2. And of course, I pulled these out of the integral because they're constants. If we do this integration, what we get is the natural log of t2 over t1 is equal to negative RCV natural log of v2 over v1. Okay. All right, and so playing around with our log rules, if we have a log and then we have some coefficient in front of it, we could actually move this coefficient so that it's an exponent of the things inside the natural log. That's just one of the properties of logarithms. No. In fact, we're also even going to move the negative sign up top. All right? And the reason, I'm writing it like this is because we know for an ideal gas that Cp, the constant pressure heat capacity for an ideal gas, is just equal to the constant volume heat capacity plus the gas constant R. Or another way of saying it is that the difference between the constant pressure heat capacity and the constant volume heat capacity is that gas constant. Okay? And so what we could do is we could rearrange this exponent so that we write it like this, 1 minus gamma, where gamma is just the ratio of the constant pressure heat capacity over the constant volume heat capacity. And because we know, in general, the constant pressure heat capacity is going to be greater than the constant volume heat capacity. So it's going to be greater than 1 here. Okay? Alright, and so we could write it like that, and we could even, just to make it even simpler, since we have natural logs on both the left and the right hand side, we could take the exponential of both sides, and what we get is T2 over T1 is equal to V2 over V1 raised to the 1 minus gamma. Okay? And I'm going to call this equation 5. Alright, and so now we have this relationship between temperatures and volumes. In fact, we know volume 1, volume 2, and we know T1. And for this 1 minus gamma thing, if we are using a constant volume heat capacity of about 21 or about 20.7 joules per mole, we could use that to calculate CP. And by doing that, just by invoking the CP is equal to CV plus R, in any case, what we get is that gamma is equal to 1.4. So once again, it's CP over CV. In any case, we have our gamma value as well, and so we have everything that we need to solve for T2. Okay, and so if you use equation 5, you get that T2 is about 755.7 Kelvin, which is 483 degrees Celsius. So the temperature jumped up quite a lot when we compressed it. It went from 25 all the way to almost 500 degrees Celsius. Okay? All right, so now that we have T2, we could, once again, since the pressure of the system is described at all times by the ideal gas law, we could just go back to the ideal gas law, plug in everything in order to get P2. Or what we could even do is we could even plug in that equation 5. I don't know why I called it equation 5. Plug in equation 2. Plug in the ideal gas law into equation 2. And we get this sort of relationship. P1 over P2 is 1 minus gamma over gamma. Okay, and so you'll notice, remember, this is flipped. P1's on top, P2's on the bottom here. And that just comes from, invoking that ideal gas law. Okay. In any case, P2 is our unknown. We know everything else. And so if we plug in, what we get is that P2 is equal to 2.6 e to the 6 pascals. Okay, so when we compress the system, we see that the pressure also increases as well. So we have the pressure for the system, we have all the temperatures, and now the last thing we want to solve for is the work needed in order to compress the system. Okay? All right, so I'm going to go to the next page for this. And so, from earlier, we saw that work is the integral of negative F system dx, and when we plugged in for the force, right, we got that this was equal to P gas times dV from V1 to V2. Okay? And if we use the ideal gas law for P gas, since this is a quasi-static compression, we just had nRT over dV over V. Okay? So that's what, the work would be equal to this. And so if we could take the integral of this, we could calculate work. But we do have a complication here, right? And that's because not only is volume a function of volume here, but the temperature is also going to be a function of volume. Okay? And so that complicates this integral. We can't, we would, since the volume is a function of temperature, right? If we plug the ideal gas law back in there, we would end up in this weird sort of like circular argument. Okay, and so we can't really directly calculate the work starting from this equation, right? And this is what happens when we're dealing with adiabatic compression, right? Specifically adiabatic, not isothermal compression, when we're dealing with adiabatic compression. All right, and so in order to get the work, what we're actually going to do is we're going to take a different approach, all right? And so what we're going to do is we're going to go back to equation 1, right, which was dt over t is equal to r over cv dv over v. Okay, this is what we have. And we could rewrite negative r over cv in terms of gamma as well. Okay, and then dv over v. And so what we're going to do here is we're going to integrate this equation, but instead of doing definite integrals, which is what we did to get equation 2, in this case we're going to take an indefinite integral. Okay. All right, and if we take an indefinite integral, what we get is the natural log of temperature is equal to 1 minus gamma times natural log of volume plus alpha, which is some constant we get from integration. Okay? All right, I'm then going to rearrange the equation by basically taking the exponential, or first moving this 1 minus gamma to be the exponent of volume, taking the exponential of both sides, and then moving the volume term to the left-hand side. Okay? So those are the steps I'm going to take. And when I take those steps, what I'm going to end up with is temperature times volume to the gamma minus 1 on the left-hand side is equal to what I call alpha prime. And this alpha prime, all it is just equal to the exponential of this alpha that I had here. Right? Let me write that better. Okay. All right, and so it's just equal to that. And so we have temperature times volume raised to the gamma minus 1. And the reason it's gamma minus 1 now is because when we flipped it over to the other side, we had to take like the negative of it, right? And so that's why that gamma minus 1 flips around. Okay. In any case, we have this relationship on the left-hand side, and what we could do now is we could plug in the ideal gas law. And when we do that, we can plug in the ideal gas law for temperature. And what we get is pressure times volume over moles and the gas constant, still times that other volume, that's still equal to alpha prime, which just the exponential of alpha here. Okay? All right, and so that's what we have here. And the one thing I want to point out now is that, alpha prime is a constant. And then for our system, the moles are constant, and the gas constant is a constant as well. So constant. This is also a constant. Okay. And so what I'm going to do here is, since I have these two volumes here, I'm just going to multiply them together. And what I end up on the left-hand side is pressure times volume raised to the gamma is equal to alpha double prime, okay, which is just nr times the exponential of the original alpha. And all these things are constants. So emphasize that again, constant. Okay? All right. And so what I want to do here then is I'm going to isolate the pressure by itself. So that's just equal to gamma double prime times volume to the negative gamma. Since I moved it to here, that puts a negative there. That's all I'm doing. Okay? Anyways, now that I have this statement for pressure, an alternative statement for pressure, I'm going to take that and put that back into the work equation. Okay? So I have dV here. But now I'm going to plug in this for the gas pressure. Gamma. Okay? Alright, and so now that I have that, this is a constant, so I could pull that outside of the integral. And then all I have to do is just integrate this part from V1 to V2. And so what I get is that negative alpha prime, which is a constant, and then if I do work out that integral, I get this. V2 of negative gamma plus 1 minus V1 negative gamma plus 1. Alright? And then I'm going to distribute across this alpha double prime. Okay? And I'm also going to multiply this negative sign by the denominator here, so that I end up with just gamma minus 1. Okay? Makes it look a little bit prettier. In any case, I have 1 over gamma minus 1, and then I distributed it across the alpha double prime. And here, for the volumes, right, I have V2 raised to the negative gamma plus 1. I'm going to split this up into V2 minus gamma times V2, right? These are equivalent statements. Because that plus 1 there in the exponent, that's just saying that, that this is multiplied by another V2. That's all that is. Okay, so I did that for the V2 term. I could do the same thing for V1. Okay, and the reason I do all that is because this alpha double prime times V2 to the minus gamma, this is exactly what we said pressure was equal to, just up earlier. And so this segment right here, this is just equal to P2. And this segment right here, this is just equal to P1. Right, and so for our work, what we get in the end is just P2 V2 minus P1 V1 over gamma minus 1. Okay? And so we get this very, very simple equation for work. Similarly, if we wanted the work in terms of temperature, we could get that. All we would have to do is just plug in the ideal gas law, right? And what we get is that work. So, just to specify, IG law, and what we get is that the work is equal to moles times the gas constant over gamma minus 1 times T2 minus T1. So actually an even more simple equation. Okay? All right. And so all these equations that I've been writing out, so I think, did I give equations 1 through 4? These are all general equations that apply to adiabatic expansions and compressions of ideal gases. Okay? So we'll later on in the course, whenever we deal with these sort of adiabatic compressions or expansions, especially when we're talking about engines, We're actually, to figure out the work, we could just jump directly back to this equation. And so for this system that we've talked about so far, we were dealing with a horizontal piston cylinder. And the last thing I want to talk about, I believe it's like part E or something, is what would happen, how would this problem change if we were dealing with a vertical cylinder? Okay, so imagine we had a gas like this. Okay, and so the major change that would happen is now when we consider the force balance on the gas in the initial state, we still have the force of the gas acting going up, or on one side of the piston, but in the opposite direction, not only do we have the atmospheric force, but now we also need to worry about the weight of the piston as well. Okay? Right, and so if piston cylinder setup were vertical, then what you get is that the force of the gas is equal to the force of the atmosphere plus the weight of the piston. Right? And so we know the force of the gas, pressure 1 times the cross-sectional area, force of the atmosphere, atmospheric pressure times AP. The weight of the piston is mpg. Therefore, what we get in the end is that pressure of the gas initially is not just the atmospheric pressure, but it's essentially the atmospheric pressure plus the weight of the piston divided by the area of the piston. Okay? And that's it. So when we do these force balances, we need to, and we're trying to figure out the force exerted by the gas, we need to consider all the forces that are acting on the gas.